it's recording. Yay. All right. So today, I've called this 2D, infinite limits and limits at infinity. This first part is going to go really quickly. So try not to answer all the questions on the homework all at the same time. That just would ruin all of the fun. Let's see here. I'm going to throw a graph up here on the screen. F of x equals 3 divided by x minus 2. So we can kind of see what that looks like. This is a ratio right here, 3 over x minus 2. And so we call this a rational function. Rational functions normally have these sort of things going on, right? And rational functions normally have an asymptote somewhere. They don't always, but sometimes they do. So f of x equals 3 over x minus 2. What do y'all notice about that graph? Where do you think the asymptote is?
Positive 2.
Yeah, positive 2. Now, why do y'all think it has an asymptote there at positive 2?
Because if 2 was your x and you put that in, then the denominator would be 0.
Yeah, if you plugged in 2, you put said 2 right there for the x, you'd have 3 over 2 minus 2. 2 minus 2 is 0, so that's undefined. Anything that's undefined is going to be going to be not on the graph. So either normally when something is undefined, you're either looking at a hole or you're looking at an asymptote. In this case, we're looking at an asymptote. So I could say, what is the limit as x approaches 2 from the right of f of x? And so let's talk about that. What is going on if this is the 2 value? As we're moving along this graph, what are we approaching? What are the y values approaching? Go ahead, say it again.
Infinity?
Yeah, they are approaching infinity. So they're not approaching any specific number. They're just increasing without bound, right? So previously we would have said the limit here does not exist by reason of unbounded behavior, okay? However, for today's homework and from now on and forever after, I will allow you to write that infinity sign right there. Have you ever gotten to write infinity on any homework problem?
No.
Maybe occasionally or whatever. It's kind of fun to be able to write infinity, because, it's a pretty neat concept. Let's go ahead and turn that into a table. I want to see what happens as we get closer to 2. So at 3, the y value is 3. At 2.5, the y value is 6. 2.1, look at that y value. Y'all see what it is? It's 30. At 2.01, it's 300, right up there. At 2.001,
3,000.
It's 3,000. Okay? And it's just gonna continue on 2.0001, 30,000.
Oh my
Yeah.
gosh.
Pretty crazy, huh? So, what does that do this?
Is decimals full of puzzles?
Well, now you're just gonna make them.
How,
Feel
like, is it
5,000.
never ending? If you think about it, is it never
It's
ending?
gonna be thousands if
Did I miss it?
You're in the millions.
You were,
Yeah, I missed it pretty quickly. Alright. 2.000001.
Oh,
Oh,
3 times 10 to the 7th. Yeah, so it gets up there
Wow.
pretty quickly. But the point is that it's approaching infinity. That would allow you to write infinity on a problem where there clearly was an asymptote. And along the same lines, we could say, what is the limit of f of x as x approaches 2 from the left? So, definitely seems to be approaching negative infinity. Would you agree with that? So we could put negative infinity. Okay. So that's all well and good. That is an infinite limit. So the limit is infinity. The other thing we're going to talk about today, though, is limits. Oh my gosh, I realized that. Is limits at infinity. So that's asking something different. That's asking, what is the limit of f of x as x approaches infinity? So in other words, as the x values get larger and larger and larger, so as we march along this way, okay, as we're going along the graph this way, for it to extend that out, what are the y values are approaching? You know, so it looks like they're going down. Are they going to go down, 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 all the way down to infinity? Or are they flattening out? And maybe they're flattening out in such a way that it actually never crosses that line. Or maybe it does cross that line, but never crosses -1. You see what I'm saying? That's kind of an interesting question. And we see lots and lots of phenomenon in the real world, things that actually exist, that follow a path like this, okay? Or something that's bounded by this, okay? You know, something that is steadily decreasing, but not steadily decreasing, but is decreasing in this manner. We want to know, you know, is it going to drop down here? Or, anyway, so we can use the graph to analyze this as well, all right? If we got a graph, let's use graph, right? So let's find out. This is why I love Desmos. There's lots of good reasons for Desmos, but one of the good reasons is just this zoom feature. I just use that, you know, wow. I'm at the 7,000, the 10,000, 20,000. It still looks like it's above there, right? Now I wonder if did it curve up, or is it just getting closer and closer to that line? You know what I mean? So let's go to that table. So there we are at 3. Let's go 30. We have a y value of 0.1. So that was right there, okay. What about 300? 0.01000604. So we're getting smaller, right? Getting closer to 0. What about 3,000? 0.001. Okay, so that's definitely smaller than 0.01. And then got some other digits after that. 30,000. 1 times 10 to the -4th. Well, if you remember, 1 times 10 to the -4th means, you know, you move that decimal over, 4 spots, which, so it'd be, it'd be 0.0001, okay? So that's getting really close to 0. Alright, I wonder if we're gonna hit negative territory. 300,000. 1 times 10 to the negative fifth. Well, I definitely see a trend here. What about y'all? Yeah. So, what do you think we should put here? What is the limit of f of x as x approaches infinity?
0.
Seems to me it's approaching 0. It's getting closer and closer to 0. Would you agree with that?
Mhm.
What about as the limit of f of x as x approaches negative infinity? So as the x's get more and more and more negative. Well, I'm looking at the graph here. Based on my handheld sketch here, it looks like it's kind of approaching 0 as well. Looking at that graph, it looks like that it does that as well. Through a quick magic of putting a minus sign in front of these.
Approaching negative 0.
It's approaching negative. Wait a second. Okay, I like what you're saying though, because there is a difference between approaching 0 from positive territory and approaching 0 from negative territory. But in the end, we're getting closer to 0. So,
It's approaching negative 0.
approaching negative 0. There is a situation in computer science that arises when you deal with binary numbers, turn everything into ones and zeros, that you have to have a problem with how do you express negative, and it's also with ones and zeros, and you actually end up sometimes with a negative 0.
Right.
And it's when you use one's complement notation rather than the two's complement notation. So it's kind of a neat thing. All right. So that's kind of a little bit of what today's lesson is about. Infinite limits, limits to infinity. The one thing we can just say is, just look at the graph. You can always use graphs for limits, but sometimes they take a while. So you got to type them in. You have to have your computer up, ready. I could look at this right here, and I could tell you immediately that it's, as x approaches infinity, that this is going to 0. Okay, and I do want to be able to teach you how to do that as well. All right, so you can just know it automatically. I also want to get it so that you can pretty much almost in your head look at this and say, oh yeah, there's an asymptote at 2, okay? Which you probably could do already, because you could say, all right, at 2, that would cause this denominator to not exist. So I'm going to show you some techniques to be able to do this even without a calculator. Go ahead.
Would it all be the same? Like, let's say, you say f of x as x approaching infinity, and like, would it always be the same? Like, would it always be 0? Or
Nope.
No. It would be
It
different?
depends on what the function is. All right, it depends on what the function is. So here we go. New problem. F of x equals 1 over x minus 1 squared. So let's see if we're kind of picking up on stuff. Do y'all think there's any asymptotes on this one?
Yeah.
Okay. All right. So when I say if there's asymptotes, you need to say, I think, asymptote happens when there's 0 in denominator. Any chance we'd ever have 0 in the denominator? Yeah, definitely. Where do you think? What x value? Yeah, 1. Okay. Because if you have 1 down here, if you plug in 1 for x, you're going to get 1 minus 1, which is 0. Absolutely. So, without even doing anything else, we're pretty sure that there's going to be an asymptote there at 1. Okay. Now then, the only question is, what's going to happen with the graph? This is a ratio. Okay. So it's a rational function. All right. And as it turns out, see if you can think through this process with me, all right? Just as a recall thing. If you have a positive divided by a positive, what sort of answer is that going to give you? It's going to give you a positive number. What about a negative divided by a negative? What kind of answer is that going to give you? also a positive number. By way of contrast, a positive divided by a negative number will give you a negative number, and a negative divided by a positive number is going to give you a negative number. Let's look at this problem. The numerator, we can see, is 1, hence always positive. The denominator says x minus 1, but that quantity is squared, okay? So, something else to remember, if you have any positive number times itself, alright? So a positive times a positive is always going to be what, class? Positive or negative? It's always going to be positive. If you have a negative number and it's squared, it's going to be a negative times a negative, which is also going to be a positive. So I can look at this and I can, something else that I can tell without even going to Desmos, I can be like, oh, this is always going to be a positive number divided by a positive number, so therefore my answer, or my y values are always going to be positive. Does that make sense? Okay. And in fact, that's true. This graph looks like that. Well, I don't know, I just gave away the whole story there because, well, hold on. I know that it looks like that. I know, but the question now is, what's going on as x approaches infinity? All right, so let's see. Limit, I'm actually going to write this whole thing down. 1 over x minus 1 squared as x approaches infinity. And we're going to kind of notice a trend here, all right? So we'll make our own little table. X values and our f of x values. So when x is 1, no, not 1, let's go with 2 since we're... Our y value would be 1 over 2 minus 1 squared. So 1 over 1 squared, that's just going to be 1. See if you can walk with this. Whatever my x value is, the number in here is going to be 1 smaller than it. So it's going to, so if I have 3 for my x value, this is going to be 1 over 2 squared. Does that make sense? Because that, the denominator is x minus 1. So when I'm at like 4, then that's going to be 1 over 3 squared. When I'm at 5, that's going to be 1 over 4 squared. When I'm at 10, that's going to be 1 over 9 squared. Yeah, okay. So that's 1 over 4. That's 1 over 9. That's 1 over 16. That's 1 over 81. And there's a pretty interesting trend here, okay? I notice the numerator's kind of staying the same. The denominator is growing, right? Now the question is, what's going to happen with the, what are those values, okay? So 1/4, I know that one off the top of my head, that's 0.25. 1/9, I also know that one off the top of my head, it's 0.1111, and so on and so forth. All the ninths are always a repeating over there. Like 1/9 is 0.111, 2/9 is 0.222, 3/9 is 0.233. It's kind of an interesting thing about those.
Do you believe that 0.999 repeating is the same thing as 1?
I'm not, no, I don't like that idea. Let's see, not 1. Well, 1 is undefined, sure. 2, 3, 4, 5, 6. Do I have 6 in there? No, I don't have 6, I have So for 5, 0.0625, 0.0625. 1/10, or when x equals 10, it's 0.01234567 Really?
What? I don't got that space.
Such a anyway,
No, 0.123 or 0.125?
1, 2, 3, 4.
it's 0.012345. It's actually that's kind of neat. Anyway,
Just abandon the 8 like that.
yeah.
679. Oh.
So all right. So what's going on with these y values?
Getting smaller and
Yeah.
smaller.
Getting
Closer to
smaller and
zero.
smaller. Definitely seem like they're approaching 0, right? In fact, if we look at the graph, yeah, it's definitely approaching 0. Okay. This is a general trend, okay, that we're going to see every time the denominator is growing faster than the numerator. That ratio is going to approach 0. Okay? So let me say that again, we'll experiment with it. If that denominator is growing faster than the numerator, okay, then it's almost like it swallows it up and it's going to make it equal 0. All right? That ratio over time is going to approach 0. So I'll write that down. If the denominator is growing faster than the numerator, then as x approaches infinity, the numerator over the denominator approaches 0. So I guess what I'm really saying is, I don't need a graph, and this is saying, Mr. Goddard, I don't need a graph, I don't need a table. I can look at this, and I can say, numerator is always 1. Denominator is growing really quickly, because x is getting bigger and bigger and bigger. Therefore, I know automatically that the limit of 1 over x minus 1 squared as x approaches infinity is equal to 0. And if you get your mind wrapped around this idea right here, you can too. You don't even need a calculator. All right? Let me show you another example.
What does it say?
I'm gonna just, so this is just a totally different side example, okay? I'm gonna show you what happens if the numerator just goes up by, like, the numerator is x, and the denominator is x squared. Let's see what happens as x approaches infinity. What happens to this ratio, okay? Now, if we're looking at it, here's the numerator, here's the denominator. Which one is growing faster, Syra? Say again? The denominator, because x squared grows faster. X squared is getting bigger, right? Okay. So when I have 1, then I've got 1 squared. 1 divided by 1 is just 1. But when I've got 2, then the denominator is 2 squared, which is 4. What's 2 divided by 4?
Oh, 2 divided by 4, sorry.
Yeah, 1/2. I'll put 0.5.
Oh.
Let's jump ahead. 5. The denominator would be 25. 5 divided by 25. 0.2. Getting smaller, yes? 1, 0.5, 0.2, Mitzi, are you seeing a pattern here? Is that fraction, is that ratio, that's what this is it getting bigger or smaller? It is getting smaller. Let's go to 10. 10 divided by 10 squared. So 10 divided by 100, that's 1/10. 0.1. 12 divided by 144. I'm gonna need you with calculators, y'all do that one. So you always need to grab a calculator. Kirsten, help us out here. What is 12 divided by 144?
0.08.
Are you a believer?
What?
If the denominator is growing faster than the numerator, then as x approaches infinity, the numerator over denominator is going to approach
Oh.
0.
Oh, okay, got it now.
So if I were to extend this over to an infinity, what's happening? It should be approaching 0.
Haha. Calculus.
Okay? So going back to our original problem, see if you can look at that numerator, look at that denominator, okay? Who's gonna be growing faster, 1 or x minus 1 squared? X minus 1 squared is gonna be growing faster because 1 is just staying at 1, not changing. But this is getting larger and larger and larger. So in sort of a competition, you know, between the numerator and denominator, the denominator's gonna win, okay? And if the denominator wins, then it's getting bigger and bigger and bigger and bigger and bigger, and you have a set number, in this case 1, divided by a bigger and bigger and bigger number, and it's going to basically end up being swallowed up, and it's gonna eventually approach 0, okay? Or it does approach 0. It never actually equals 0, as we can tell from the graph, it just gets closer and closer and closer, but it, without ever actually touching it, but that's the trend, okay? So, if the denominator is growing faster, then our ratio approaches 0, okay? Now you might say, okay, Mr. Goddard, what about if it's the other way around, right? What if the numerator is growing faster than the denominator? Well, let's go ahead and do an experiment before I tell you. So, let's do fraction here. I'm gonna say, 3 times x in the numerator and x squared in the denominator. Now I am gonna kind of rely on y'all to talk to me. Do you know what those two graphs look like? 3x and then x squared? You might not. I mean, this is a thing that I don't know if everybody immediately has in their head. Do you know that x squared is growing much, much faster than 3x? Let me show you, because this is something really worth looking at here. So, there's 3x. Oh, that's pretty good. It seems to be growing pretty quickly. There's x squared. What's that?
Shoots up.
Yeah, it's almost straight up, right? Look at that. X squared, by the time we're like right here, the 3x is here in like the 20s, but the x squared is already up here like in the hundreds. And it only gets worse. That is to say, he pulls away and he just keeps on growing, you know. I mean, this is, by the time we're over here,
Long.
you know, if I were to say like 500, 3x is at 1500.
It's to run
X squared is at 250,000. Yeah, pretty good, right? So now let's see what happens. Now wait a second, 3x over x squared, who's growing faster there?
X.
The numerator or the denominator?
Denominator.
The denominator, that's exactly the same as that other case I just had up there. We need something that, sorry about that. We need it switched, don't we?
Purpose.
We need, what happens if the x squared is up there and the 3x is down there? Sorry about that. So, 1 squared is 1. So, try to figure out what to do. So, when x equals 1, we have 1 over 3 times 1, so 1/3. So 0.33 repeating. When x equals 2, we have 2 squared in the numerator, which would be 4. And we have 3 times 2, so we have 6 in the denominator. What's 4 over 6, class? 0.66. Let's 2 points doesn't really make a trend, but let's analyze what's going on from here to here. 0.33 to 0.66. Going up, going down. Going up. Let's jump ahead. X equals 5. The numerator, it was going to be 5 squared, so 25. Divided by the denominator, 3 times 5, so 15. With calculator, 25 over 15. 1.66 repeated. Seems to be going up, doesn't it? Let's jump a little farther ahead. X equals 10. 10 squared, that's 100. Divided by 3 times 10, divided by 30. Okay, I know that one, right? 100 divided by 30 is 3.3 repeating. Ladies, what seems to be the trend here?
It's growing.
It is growing. All right. Let's try 50. I'm gonna need help here. 50 times 50. 50 times 3 is 150. So 160 maybe? 16.666. Alright. So riddle me this. If the numerator is growing faster than the denominator, then that fraction is approaching what? 0.3, 0.6, 1, 3, 16. Seems to be getting larger and larger, wouldn't you say? Seems to be approaching infinity. We'll put it here and then we'll graph it and see if we're right. If the numerator is growing faster than the denominator, then as x approaches infinity, the numerator over the denominator also approaches infinity. If the numerator is growing faster than the denominator, which is that's what we saw right here, x squared is growing faster than 3x. Then as x approaches infinity, the numerator over the denominator approaches infinity. So I'm going to actually graph this, x squared over 3x. And here's the graph. Now let's look at this. As x gets larger and larger, as x approaches infinity, what's happening to my y values? They're getting larger and larger, aren't they? Absolutely. Okay? So here's the thing. And by the end of tomorrow's lesson, you'll be able to do this as well. In fact, you might even be able to do this right now. If I were to say, what is the limit of x squared over 3x as x approaches infinity? I can look at any of these fractions and I can be like this. I got this. X squared versus 3x, x squared wins. The numerator wins. So therefore, since the numerator is growing faster than the denominator, that's infinity. Done. Okay? Bitsy, let me say that one more time. I can look at this right here, I can say, the limit of x squared over 3x, who's going to grow faster, x squared or 3x? X squared is growing faster. Therefore, numerator wins. As x approaches infinity, this whole fraction is going to approach infinity. Done. Numerator wins, go to infinity. Denominator wins, I go to 0. Okay? It only gets to be a problem if you look at that homework that I gave you. That is to say, not really a problem, but becomes kind of weird, is what if I've got other stuff kind of messing around there, like plus 3 and plus 2x, and if I've got minus signs and all sorts of other stuff in there. See what I'm saying? That's kind of a question mark, and so that's what we're going to wrap up tomorrow, okay? So, as far as this homework goes, you can definitely take care of all of the graphs, no problem. The ones here at the end where I don't have any graphs, that's what we're going to finish up talking about tomorrow. Alright? Sounds good. Today we talked about infinite limits and limits to infinity. Thanks for watching. See you next time.